The agenda is briefly indicated here. So we'll continue our discussion regarding regression. And earlier we did talk very briefly about simple linear regression, but we'll spend some more time. And we'll also talk about fitting a line, which is regression line, to a data set and other related things. The name simple in this simple linear regression, when we talk about simple, is basically when you have only two variables. So when you have one independent variable and one dependent variable, that's the simplest case. So simple refers to that situation where you are only dealing with one independent and one dependent variable. And we are also referring to linear, so we are still working with the model that is linear. So if you look at this simple linear regression model, the equation looks like this, where y is the dependent variable. It depends on x, so that's why it's called dependent variable, and x is the independent variable, and they are related to each other in a linear fashion, and we capture that linear fashion or linear pattern using these two parameters, beta 0 and beta 1. As you know, whenever we use a Greek alphabet, basically we are referring to some population parameter. So these two are referred to as the parameters of the model, and these are related to the population parameter in which we are interested, and we try to estimate them using our data. And then there's also epsilon, and this is a random variable or the error term in our model. So a model has like mainly two major components. One is the explained part that can be explained using a variable like x here, and whatever x cannot explain, that becomes the part of error. So why that variability occurs, we cannot pinpoint and say that this is because of this. There are a lot of terms used for that, but most common one is statistical error. So simple linear regression model has mainly four assumptions that we work with, and you'll also notice that all the assumptions are related in some way to the error. So the first one is mean of error at each value of independent variable, which is x, is 0. It may not be exactly 0, we can say approximately 0. And this is the popular linearity assumption. We assume that linearity assumption is there and it is satisfied if the mean error at each value of independent variable is 0. And then these errors are independent. Error is basically the difference between a predicted value and the actual value, and simple linear regression model will be valid only if these errors are not related to each other. They don't form some kind of pattern, but they are independent. Errors at each value of independent variable are normally distributed. So if you make a histogram, if you have sufficient data, it should look like a inverted bell-shaped curve. But if you do not have a lot of data, you can always make use of normal probability plot or QQ plot, which is the same thing, and that can indicate whether the pattern is linear or not. If it is linear, it means normal distribution assumption is valid. Fourth one is errors at each value of independent variable have equal variance. So around that regression line, if you see a uniform band, it will not be always be exact. There may be some ups and downs, but if you do not see a very obvious change in variability, that will mean that this assumption is satisfied. But all these four assumptions can be combined into one simple sentence, which is indicated here, that errors are independent normal random variables with mean 0 and constant variance sigma square. Some unknown variance, we don't know how much is that, and obviously it will vary from data to data. But this statement combines all four assumptions that you see above. So let's look at some examples of linear relation between two variables. And in these examples, I have used the patterns to also indicate strength of the relation, and also direction in all these cases are positive. Like one goes up, other goes up. So the two variables are directly proportional to each other. So if you look at this first one, the independent variable which is on the x-axis and dependent variable on the y-axis, so they seem to follow a very broadly like a linear pattern, although there's a lot of variation around this line of best fit. And you also have the equation here. And because there is a lot of variability, our R square, which is coefficient of determination, is only about 11.5, which means 11.5% of the variability on an average in our output is explained by this model. So that means the explained part is like quite small. So even if you round it to 12%, you still have 88% of variability which is unaccounted for or unexplained. But if you look at this second one where we say moderate positive correlation, so you can see the spread is now slightly lower than the first one, and R square now is about 36.9, so roughly 37%. So 37% of the variability in the output on an average is explained by this linear model. But it still has more than 60% unexplained part. And then we have this strong positive correlation where all the dots are quite close to the straight line. Because you have less variability around the line, R square is the highest. It is 7.6, roughly 88%. So only 12% of the variability is not explained. And this is opposite of the previous one. So now the direction has changed to negative. We have weak relationship. R square is only 11.5%. Moderate, R square 0.36. And then we have strong with about 87.6%. It may not happen in real life or real data, but this is a situation more from like theoretical point of view. So if you look at this first plot, and if we were to draw a straight line passing through these dots, we'll find that all these dots are exactly on the straight line. So that means all the variability in the response variable y is being explained by the straight line model. So if you calculate R square, you'll find that it is 1 or 100%. So 100% of the variability is being explained by this first one. There's also something called correlation coefficient. Another way of calling this is coefficient of correlation. So both are same thing, either correlation coefficient or coefficient of correlation. Whereas R square is coefficient of determination because it determines how much variability is being explained. So you'll notice that for this perfect correlation where there is no variability, R square is 100%. And when you have negative correlation between the two variables, like one goes up, the other comes down, so there also all the values will lie on a straight line, and if you calculate R square in this situation, you'll get exactly 1. Because there is no variability around the line, all the dots are, or all the data points are exactly on a line, no variability, no unexplained part. So R square is 1. But if you calculate correlation coefficient, because there is a negative slope, this time R is going to be -1. So in a way, R square gives us just some information about how much contribution is there by the model in terms of percentage, which is very easy to understand for anyone. But R can also give you more information in the sense that it also tells you the direction of the relation. Is it positive or is it negative? R can be obtained simply by taking square root of R. But then for direction, you will have to look at either the regression equation or sign of the slope. So if slope is positive, then you have this situation. If slope is negative, then you have this situation. And when there is no obvious pattern and all the dots are spread around in that box, so approximately R is going to be 0. R square also will be 0. And there is no correlation between X and Y. So this is a small table that gives us rule of thumb in terms of the values. If the value or the magnitude of R lies between 0 and 0.2, so 0 is obviously no correlation, but when it starts to increase, we may see some weak relation between X and Y. If the values are between 0.20 and 0.40, relation may be said to be weak to moderate. 40 to 60, medium to substantial. Usually 60 to 80, it's very strong, and anything between 80 and 1 is extremely strong. So it is true about both in the positive direction or negative direction. Although I have indicated only positive values here, but the same thing is true for negative direction also. What value of R we get usually will depend on the application and where the data is coming from. So for example, in physics, where you have very good equations like V is equal to IR or E equals mc square. So in those situations, if you are doing any calculation, you may get values which are on the higher side. But in business, there are many occasions where it's not possible to get high values because processes may have high amount of variability. And especially in social sciences, even getting a 0.2, 0.2 sometimes is a good achievement. So it's not that something is good or bad. It totally depends on the application and the data we have, and the nature of data dictates what we may be able to get, and then we have to work with that. So it's not feasible to always get something above 0.8. So the equation that I showed you earlier was for the population where I used beta 0, beta 1. But when we use data and we calculate these estimates, small b0, small b1, so that's the estimated simple linear regression equation, where b0 is the y-intercept of the line, b1 is the slope, and we use a hat symbol here at the top of y to indicate that this is the estimated value based on the equation or predicted value. So for any data, if you have some scatter plot, and it shows some somewhat linear trend, so we can always use a straight line to represent that data. So this straight line becomes our model. But theoretically, you can draw so many straight lines. There's no limit to how many straight lines you can draw through these points. And each line may have some capacity to represent your data and give you a decent outcome. So people have found that we should go with that line that minimizes square difference between yi and yi hat. Now, what is yi? Each data point is a yi. So suppose this is x and this is y, and we have some data points and a straight line. So this line is the predicted line or our y hat with the b0 plus b1x equation. So for any xi value, like let's say this value here, so if this is xi, I means ith value, then the predicted value for this is this equation that we have for y hat, and we will predict our y hat based on this. So the difference between the actual and the predicted value, this is y hat, which comes from the line, and this is yi. And when you take the difference between the two, that's the gap or the error part that we have. And least square method basically says if we minimize the total of these squared errors, so you take this distance for each and every data point, and if you are able to minimize it, that line is the best line. So that's the line of best fit. Finding that line is very easy. With little algebra, we can find out that if we use this formula for b1 or slope, and if we use this formula for the intercept, that's going to minimize the square deviations between actual y and predicted y, squared of that. So basically, these two formulas ensure that we are using least square method, and they are called least square because we are using this criteria, and that's what gives us the regression line that we usually use in most of the situations. So this is one example that we used in one of the classes where we used roller data. We had a variable called roller weight, and then dependent variable was depression on the grass. So how much the roller weighs versus how much depression we get on the grass. If you only look at this scatter plot, we can make some simple observations. Like scatter plot suggests increasing linear relationship between roller weight and grass depression. Also, no unusual data points are detected in this data set. So we don't have any data point which is like very far away from the line, maybe like something which is here or something which is like very far away from the line of best fit. So basically, unusual data points refer to the outliers. So we don't see anything like that. It also indicates a variation around the estimated regression line to be approximately constant. If you think of this as a band, so variability around the middle line, that blue line, is basically roughly around these two. So it seems to be uniform. So if we use the roller data, we can very easily estimate our B0 and B1 that we need for the equation, but we also get a lot of other information, as you can see. Apart from estimate of intercept and weight, it gives us standard error for the intercept. So this 4.7543 is related to negative 2.0871. It also calculates a t-value. It uses t-distribution basically so that we can do a t-test and find out whether the intercept term is statistically significant or not. So clearly, based on p-value, we find that actually intercept is not statistically significant, but weight is statistically significant. Now, what is the meaning of intercept. So if we have an equation like this where y equals b0 estimate of intercept and b1 estimate of slope times x. So intercept is the predicted value of dependent variable when x equals 0. So if this term is removed, if we replace x by 0, so this whole thing becomes 0, and then we have y equals b0. But one thing to remember is that it is only meaningful when x can actually take values close to 0. It doesn't happen all the time. It doesn't happen all the time that x values are close to 0. It totally depends on the data. For example, if x is a number of iPhones sold, which may be in millions, and y may be profits made by Apple in terms of dollars, so x values are going to be very, very far away from 0 because those numbers are so big in millions that 0 is going to be very, very far away. So intercept is only meaningful when x can take values close to 0. So if you look at our equation, I just picked up value of intercept from that summary table, and same thing with the slope. So we get this straight line equation. So we can say when roller weight is 0 on an average, the depression will be negative 2.0871. So that's the interpretation of intercept. Obviously, roller weight is not going to be 0. So this is not very meaningful because roller weight is unlikely to be 0. And in many cases, people also actually do away with the intercept. If we have a situation where intercept is not really needed, like when x equals 0, y should be equal to 0. Because if Apple is only looking at profits by iPhone, and if we are only relating those two things, so if they do not sell any iPhone, they cannot make any profit. So profits are going to be 0. So sometimes we may force a line to pass through the origin, and to do that, we have to eliminate the intercept. So basically it becomes 0. So we are going to look at one example of that too. But let's look at slope. So slope is the average change in y when x increases by 1 unit. So one thing to emphasize is that we are talking in terms of average. We are not talking in terms of like individual values. So if you look at our equation, we can say for every 1 unit increase in roller weight on an average, depression on grass increases by 2.6667 units. So we don't have the actual units, whether it is in millimeters, centimeters, inches. So I'm just saying units, whatever may be the units of depression be. If the slope was negative, then instead of like increasing, we would have said decreasing or decreases. Now another thing to note about linear regression is predicting y beyond the range of x is not advisable. Due to lack of any evidence, in statistics evidence always comes from data. So if you do not have data beyond the range of x values, we should not try to predict something because we don't know whether the relation is going to remain linear or not. So we cannot extend this line something like this and try to predict what will happen if the weight of the roller is outside the range. So we cannot say it is likely to be this because we don't know whether these dots will continue in the same direction, or sometimes there's every possibility that they may change the direction and become non-linear beyond the range we have data. So we should not be using linear regression line to make predictions for future. So you have seen this kind of plot. Once we have our simple linear regression model, we make several plots. One of them is residuals or errors versus the fitted value. So residual is basically your yi minus y hat. First one is actual value or the observed value, your data point, and y hat is the predicted value based on this line that we have. So many times actually even you don't have to wait for these residual versus fitted lines, because many times scatter plot itself will start indicating, if you look carefully, what is likely to happen. So if your data points are not linear and they are like somewhat non-linear, then it will show up in the residual plots too. But if you look at this, we see that the residuals are distributed randomly about the zero line. This dotted line is the zero line. What it means is if there is a data point which falls exactly on the blue line in the scatter plot, so that will fall exactly on this dotted line in the residual plots, because there is no error. Y minus y hat will be 0. For any data point that is exactly on the blue line in the scatter plot, error is 0. So residuals are distributed randomly about the line. So if you look at the dots here, very broadly we can say, especially with small data, we cannot read too much into it, but we don't see any obvious pattern. Another thing you'll note is, if you look at the fitted values, which is like your depression or the dependent variable values, so this first value is very close to the zero line. And where is that first value in the scatter plot? You see this depression is like less than 5. So that's the first value, and that's what you see here. This dot is very close to the blue line or our regression line. So that's why this dot on the residual plot is very close to the dotted line. If you look at second dot here in the scatter plot, so that is slightly far away from the regression line, and that's why you see this one is slightly away from the dotted line. So these first 4 values that you see here are these 4, and these 2 that you see are likely to be these 2. You can see one is above the line and other is below the line. So one is positive, there is a positive error, and there is a negative error. You can also use this for checking whether the variability is changing or not. So although it is also visually can be seen from the scatter plot, but here we can see residuals roughly form horizontal band around zero line. So we can say equal error variances. So that assumption is not really in danger. And also we do not see any outliers. We don't see concentration of data at one group and then there is somebody sitting very far away from them. So we don't see that kind of situation. Although R always tells you or labels by default 3 data points in any of the residual plots. So it says 5, 7 and 8th data points are these 3. So I have put a note here. With the residuals, we should avoid over interpretation. We should, sometimes the tendency may be to look at like something which doesn't exist. For example, I'm just hypothetically saying, if I ignore this point for the time being, it may look like that there's a pattern here. Something like this. So that will obviously be over interpretation. And especially with less data, we should not do over interpretation. So our roller data is from the AG library. The data is called roller, weight and depression, plot depression, and let's call our model M. So that's what gives us our output that I was showing you. You can also use AB line M to draw that straight line. And then, so if you want to plot those 4 plots 2 by 2 in 2 rows and 2 columns, so we can use this and simply say plot M. It gives you the first plot that I was showing you. Second plot, look at the tails. Sometimes it's difficult to understand whether it is really normal or not, and especially it's very subjective. It doesn't tell you like one answer. It is up to you how you do the interpretation, how you look at that plot and decide whether it's really normal or not. One way to calibrate your eyes to look at these kind of plots is to see some more examples. So for example, in some industries, especially final inspection, they have visual inspections about like looking for some defect or some problems in a product. So to calibrate those people who are doing the inspection, they make pictures of like how a defect looks like different pictures, so that they can always refer to it and then decide, okay, this defect is okay, we can let it go, but this defect is not okay, we should reject. So similar concept we can use here. So let me copy this part and return to 1 1, and then we'll use Q reference residuals in M. So our model is in M. The total number of samples including reference samples and test samples if any. Let's use 8. And then how many rows we want. In the PowerPoint I used 2, so I'm going to use 2 here also. So the blue one is our data. How many data points we have? We have 10. So other ones are also with 10 data points, selected randomly from normal distribution. So you can see, although this is like straight, this seems to have a curve, but still this is coming from normal distribution. So there's no reason to believe that this is not normal. Every time you run, the pattern will change because it will randomly get data from normal distribution and present some samples here. If this is normal, we cannot doubt the blue ones to be not to be normal. So you can see how normal patterns behave with only 10 data points. So every time you run this, you get a different random sequence. So this is how this was generated, and the idea is to calibrate our eyes so that we can decide whether this is really normal or not. Just to give you an example with the bigger data set and another data, that data set gave these 4 plots. So if you review the first plot, residuals versus fitted line, we have this dotted line here in the middle. But you can see the fitted versus residual, there is a very clear-cut pattern, non-linear pattern. And another thing which is very obvious from the first plot and also this one is that the variability is not within same kind of range. So you can see there's a lot of variability here. So if you assume this rectangle to be the box, which indicates uniformity, but you can see there's a lot more variation here and lot less variation here. So variability also has a problem. So we want the variability to be uniform across the fitted values. That seems not to be happening here. In terms of normal distribution, may be difficult to say much. So more or less maybe normality is being followed, although like there's a lot of deviation here compared to the dotted line. in terms of outliers, one of the points which is indicated is 334th data point. So that data point looks very lonely and sad, like away from the community, as if nobody cares about this data point. So same thing is highlighted here. Now the question may be whether this data point is like something wrong with this data point. If there is access to that data, to go and revisit and see if there was any data entry error. So for example, if you have data on, let's say, mileage of cars, most of the values are up to 150,000 miles. But then there's one car where the value is very different, maybe 700 million miles. So clearly there may be something wrong, because something happened where the person who was doing data entry, instead of entering the mileage, entered his or her phone number. And that basically came out here in this plot, that it doesn't belong to the group, it stands out in some form. So there's always a way to investigate and see whether it is real data or it needs correction or we need to delete. But if you look at the fourth plot, where we see whether any single data point in terms of Cook's distance has a huge leverage on the regression model, we don't see this 334th data point. Although it is flagged in two plots, but if it is not having a huge impact on the model, so it may not be creating any problem. Even if it is there, even if we are not able to investigate and we don't know the source of like how this data was collected, so even if we have to leave it within the model, it's not going to harm us in a big way, because the fourth plot doesn't flag it.
Prof. Rai, can I very quickly?
Yeah.
On the previous slide, there were differences in terms of the outliers, like you have 334 on your residuals versus fitted scale and location. However, in the leverage is 117. How do we interpret that, or what's the order of priority to read it?
Yeah, so for outlier, usually the problem comes when the outlier has a large influence on the model. So if there are data points and there's one data point very far away, especially on the extremes, it will try to pull that regression line towards it. So what will happen if it tries to pull that line towards it? It will change its slope and also its intercept, very likely. But it doesn't look like, based on the fourth plot, that 334 is causing anything unusual in terms of like it's using its muscle power of being outlier to move the line in some significant way. And the reason could be like if our data points were only 10 and one was like very different from others, so that would have had big impact. But in this case, probably we have more than 500 data points, and one is not able to really have that much of influence. That's why it's not appearing here. So that's why sometimes like multiple charts can highlight these kind of things. So okay, 334 looks very different in terms of residual. It has a high error on the higher side based on the first plot. But then is it creating a problem when it comes to leverage or having a big impact on the model? That's not happening in the fourth plot. So that means one, like we need not worry too much about it. It's not really affecting our slope estimate and intercept estimate in a big way. Very broadly in terms of like where the problem is, and that 334 is not a problem. In this situation, The problem is not with 334. The problem is like different. The problem is that there is a very clear-cut pattern here. So that means the explained part of the variability is being explained not to the best possible extent. There is a lot of potential that we have overlooked, and it has gone into the error. So whenever you see a pattern in errors, so that means there is possibility of extracting some explained variability and adding it to our model so that the model can better explain the variability. So that potential exists here because there is a problem in terms of the pattern. But the other problem, although like we see, we can ignore because it doesn't really change our model in a very big way.
At this point of the course, are we expected to remove outliers or not? And the other question, if we do, what's the best practice to remove outliers?
So outlier, we should not close our eyes and just remove, because especially in future chapters we'll see where you have like more variables. So right now we are only doing simple linear regression with only two variables, x and y. But when we have multiple linear regression and when you have 10 variables, like I have seen data sets with 1500 variables, so there it becomes very important topic, because you are not removing one data point. You are, if you have 1500 x variables, if you want to remove one row, you are removing data from like so many other variables also. So you are throwing good data with just one bad data. So there obviously we have to come out with some strategies, but the simplest thing is to investigate, go and investigate why that data is so strange, and is there any possibility of correcting it. If it is possible, like for example, if mileage values are well within 150,000 miles for a car and we see 700 million, so obviously there was some typo or typing error. So one way to handle that could be find the average of similar cars and use that average instead of that 700 million value, which was probably some kind of phone number and it was entered by mistake. So different strategy can be drawn in different situations.
Thank you.
Now, if I do not know what to do with the outlier, and if this 334 would have appeared here in the fourth plot in such a way that it has a huge Cook's distance and it has big leverage on the model, it has a big impact, a single point having a big impact on the model, and it looks very different. So that would have made it a candidate for removal, at least from this model where we have only two variables, one is x, other is y, and we don't lose too much. So that would have been a candidate for removal. Yeah. So we'll do some simulation to just look at few things. Suppose in x, random variable x, which is an independent variable, we put random numbers from standard normal distribution. Let's go for 100 values, and then we create y, or the dependent variable, which depends on x. And suppose relation between x and y is such that, so this is not coming from data, now we are creating a model, so such that intercept is 10 and let's say slope is about 5 times x. So now x and y are obviously related, and if you want to plot y as a function of x, you will notice that because there's no error, so this is simply a straight line pattern. If you do the linear model, y as a function of x, and do a summary, what happens to the summary? So intercept, so this is 10 actually, because 1.0 into 10 to the power of 1, so that's 10. Because there is no variability, intercept is 10, we can see, and slope is 5, R square is 1 because now the variability in y can be explained on a 100% basis. There's no error, so obviously R square will be 100% or 100. And if you calculate coefficient of correlation, that will be +1. It's a perfect correlation between x and y. So there's a warning message also that it's essentially a perfect fit because there's no variability. So it says summary may be unreliable. We don't expect this in real life, so this is only for like academic purpose, but it tells you that there may be some problem. If you want to add line, you can add that line, straight line, in a different color. Now if we introduce a variability, that error term in y, let's say again we use random normal distribution and get 100 values from standard normal distribution with mean 0 and 1. We are saying that this is a random error. So remember, one of the assumptions is that errors are normally distributed with mean 0 and whatever sigma. So sigma doesn't matter, mean should be 0, and for standard normal distribution mean is 0. So this will satisfy assumption of normality and equal variance. So if I run these once again, all these, this is what you get, this straight line equation. But now after introducing this variability using this, now you'll see that the estimates are not exact. So you can think of 10 as the population parameter. So we know because that's how we create it. So beta 0 is 10, but our estimate based on 100 samples says that it is 10.1. So it deviates a little bit. Similarly, instead of 5, now we have slope of 4.9. And R square has come down from 100% to 96 because you can see there's a variability around that straight line. But if I run this whole thing again, just notice what happens. So data points change. Not a huge change in R square, still 96%. And the values are also close to 10 and 5. But data points obviously change because line number 16 and 17 is giving you a random sample of 100. In R, if you want to freeze that randomness, if you want to get same plot again and again, the way you can do is you can use set.seed. It doesn't matter what number you use, as long as you are using the same number, you get the same plot. I'm just using number 7. And if I run this whole thing, we get this plot. If I run it again, it doesn't change. So at least that randomness is fixed. So this was with error term where error follows normal distribution with the mean 0 and sigma 1. But what if I make a change? Let's keep mean 0 because we have to satisfy that assumption. But we change standard deviation to 3 now. Instead of default 1, we increase it. So obviously you would expect the variability to be higher now, and R square, which is like 96%, to fall down little bit. So if we run this, you can see now there's more variability, but still a linear trend, and R square is only about 74%. Only 74% of the variability is being explained by the model, and estimates are quite close to 10 and 5. They remain close to the actual values, but now we have more unexplained part, more variability. If you increase it to 5, your R square will further go down and variability will increase. So this is with sigma of 5. So now R square is only 51%. So very high variation around the straight line. The way I constructed this we are trying to make sure that we are not violating any of those four assumptions, whether it's linearity or constant variability and things like that. So if you do that plot, so I'm going to just copy 2 by 2 thing. So there may be some ups and downs around the dotted line, like this red line shows slight increase and slight decrease, but we know that we did not violate any of the assumption. So little bit of ups and downs are okay. So it also says this 71th and 91. So it points out that these are like extreme data points. And in terms of Cook's distance, 57, 89, and 91. Now let me deviate from the linearity. So basically I'm trying to defy those assumptions and see what happens. We had kept the random error term independent of others. So now let's multiply this by maybe a fraction of, I would say maybe 0.2 times x times. So now it's not like independent, it is related to x in some way. We can actually go back to maybe 3. So let's see what will this give us. So first of all, this is our scatter plot. We were trying to violate our assumptions, but we did it mildly. So let me try a bigger number so that things become more obvious. Okay, the way it is working, there's less variability in the middle and more variability on the sides. That is also getting reflected in the first plot. If you see, it is much wider at the ends. So variability is much higher as you deviate from the middle. When you go below 10 and above 10, variability starts to increase. So clearly it doesn't remain constant. And that one is highlighted in scale location plot very clearly, that as you deviate from 10, you are getting a V-shaped variability. In terms of Cook's distance, we still don't see, like, these dotted lines are now into our radar, but we don't see any point like crossing them. So we don't have any single point which is going to spoil the entire model. But model itself is faulty now because you see all kinds of problems happening in the first plot, third plot. And I would also say normal, no more tail, but major part of the tail is starting to deviate. So there are clear violations of those assumptions on which a simple linear regression model is based. And how it happened? It happened because now your errors are not independent. They are dependent on the values of x. I'm going to copy this just below. And I want to remove this error term. So let's try x times x. Now we don't have a linear model. So if you go one by one, plot, clearly this is not a linear model. And if you try to fit a linear model, it is going to fit a linear model, but you can see that it's not really valid. So usually when we apply any regression model or linear regression model, we never start by running the model first and then try to find out, like through residuals, if things are okay or not. In regression analysis, first step is always to do a scatter plot, and that itself will tell you whether you really should proceed any further or not. So clearly here, building the model is not going to be useful. Although your R square is 19% and it says that slope and intercepts are significant, statistically significant, but it's meaningless. It's not a good model. And you can see very clearly some kind of pattern forms in the plots indicating that the model is not appropriate. Assumptions are getting violated. Okay, so coming back to our roller example, we had these 4 plots, and these dotted lines, you can see there's one data point on the boundary line. That's going to happen with small data sets, but there's not much to really worry about. Another thing I want to add here is analysis of variance that we briefly saw earlier, and our model is in M. I can simply run ANOVA and M, and that will give us analysis of variance table. So response variable is obviously depression of the grass, and our model is based on one variable. In this case, it is weight of the roller. So this column that you see, DF, stands for degrees of freedom, and the reason it is 1 is because we have only one independent variable, weight. So in this data set there is only one independent variable, which is weight. That's why we have a degree of freedom 1. And for simple linear regression models, if you do ANOVA with simple linear regression model, degree of freedom for that variable will always be 1. It is always going to be 1. Residuals or errors, they have degrees of freedom of 8. So how it is calculated? It is calculated as sample size minus 2. Somebody may say, why 2? Why not 1 or why not 3? So sample size minus 2. 2 because in our regression model, we have two parameters that we are estimating. One is intercept, other is the slope. So whenever we have to estimate two parameters, or number of parameters to be estimated is 2, then we have to subtract 2. So 10 minus 2 gives you 8. If you had a situation where there was only one parameter to be estimated, like you don't want intercept and you want intercept to be set to 0, so in that case you'll do n minus 1 because you want to estimate only 1, so your degrees of freedom will be slightly higher. But in this case it will be 8, so the total degrees of freedom, 8 plus 1 is 9. So total degrees of freedom is always sample size minus 1. So we have 10 samples, 10 minus 1 is 9. And then you have a sum of squares. So sum of squares in a way capture variability in the data. And this part is variability captured in terms of sum of squares due to the regression model. So relation between depression and weight. So that is contributing about 657.97. And the error or residual is contributing, thankfully it is contributing less, 362.93. If errors are high, then the sum of squares also will be higher. When you add 657.97 and 362.93, you get total sum of squares. So in the sum of squares column, if you add the 2, that will give you a total. So let me switch to our PowerPoint. Mean square you can think in terms of variance, S square. So S is standard deviation and S square is variance. And the formula for variance is, so total of yi minus y bar, which is the average, square divided by n minus 1. So that's the formula for the variance that we calculate from the data. Yi minus y bar whole square divided by n minus 1. So this numerator is nothing but sum of squares. This symbol means sum, add everything that comes in front of it. So all yi minus y bar squares are added. So because we are summing all the squares, the numerator is called sum of squares. And in the formula for variance, the denominator is called degrees of freedom. We always divide the numerator by the denominator. And denominator is degrees of freedom, and that gives us the variance. Exactly same thing or same concept we are using when we are calculating mean square. So we divide sum of squares for the regression by its degree of freedom. Now for simple linear regression, this is always 1 because we have only one variable. So degrees of freedom is always 1. So when we divide sum of squares by 1, it remains same. And it only happens with simple linear regression, where sum of squares for the regression and mean square are same values because it is being divided by 1. When you divide sum of square for error by its degree of freedom, you get mean square error. So now you have two values. The first value is the variability because of our model, where the variability is explained by a variable called weight. So that part, and then you have unexplained variability. So what is unexplained variability? Which is not basically captured by the model. So when you have error or unexplained variability, and then you have a chunk which is being explained by the model, you should expect, if your model is worth anything, you should expect this mean square due to the regression to be much higher than the error. If error and that number are equal, obviously there is no value in that model. So you want first number to be much bigger if your model is really useful. So that's why in the next column, where you have f value or f ratio, we divide first number by this. And if your number f value is less than 1, it means that the variability contributed by error is even more than the model itself. So basically saying your model is worthless. So f value, if it is less than 1 or even 1, it's of no use. So f value is going to be useful only when it is greater than 1. Now, how much greater is good? It totally depends on like how much data you have and what is the kind of variability that we see. So we'll leave that part to the f distribution, and we come out with a p-value that we are familiar with, and p-value tells us that actually it is significant. This 14.503 as f ratio based on f distribution looks like it's statistically significant. So that means our model has some worth. The model is useful. So first column in ANOVA is always source of variation, where that variation is coming from. So the total variation in our case is broken into two. One is based on our regression model, and the second one is unknown, unexplained. We don't know why that variability comes. So that goes in residual error. So degrees of freedom always 1 in simple linear regression, but you'll see with multiple linear regression, it is basically number of independent variables. Residual error in the ANOVA table is n-2, sample size -2, and total is always n-1. So anytime you have like other two available, and if the third one is not available, you can always calculate, because the total is always n-1. SSR is sum of square due to regression, sum of squares due to error, sum of square total. And then we calculate mean square column by dividing. You can say this is like 1, 2, 3. So fourth column is equal to column 3 divided by column 2. So basically sum of squares divided by degrees of freedom will give you MSR, MSE, and these two can be used for estimating your F value or F ratio. And I mentioned that for linear regression, these two cells will be same because of 1. Let me run this summary once again, just so that they are side by side, this one and ANOVA, and look at them. So in this summary, you will see there are some parts of ANOVA already reported. F statistic 14.5 So that's the same value as this. So this is coming from your ANOVA table. This F statistic is based on 1 and 8 degrees of freedom, which is coming from here. This p-value of 0.005175, so same thing actually. And once again, only for simple linear regression situation, this value that you see from ANOVA table is same thing that you see here. Not only that, for simple linear regression, actually F distribution and T distribution, they are related to each other. This p-value was based on a t-value of 3.808. Let me copy this 3.808 and square it, like 3.808 times 3.808. You get 14.5. So this is exactly same value. Your F value is nothing but square of the t value that you see here. So once again, this is only like special case situation where we have simple linear regression where there is only one x variable and only one y variable. Total sum of squares is SSR plus SSE. Now what exactly is SST? Total sum of squares is yi minus y bar whole square, and total of that sum of squares due to regression is, so y hat is our regression line minus average whole square, and error is each and every response value minus the predicted value whole square. That's what gives you error. This is the explained part of the model, and this is the unexplained part. This is the explained part, and this is the unexplained part. So these are like side by side. What are we testing? We are testing if beta 1 is 0 or not. If the slope, this slope is different from 0, like statistically significant basically. If it is different from 0, it means it is statistically significant, and we do reject null hypothesis. So that means this is not true. So it is statistically significant. So for simple linear regression, p-values are same. This is same as this. For simple linear regression, square of t value equals f value. So I mentioned that. So square of this is basically your p value. So somebody would say, if I can do this hypothesis testing for the slope or even the intercept using this table, why do we need ANOVA? Is it adding any value of any sort? My conclusions are basically same whether I look at the top part or the bottom part. So my conclusion is that this model is statistically significant. So why use the ANOVA table? I think that criticism could be valid only for simple linear regression where we have only one x and one y variable. But F-test, you'll see that it becomes more and more useful when we start talking about multiple regression where you have more than one independent variables. So how do we calculate coefficient of determination R square? R square is nothing but SSR, sum of squares due to regression, divided by SST. So if you go back to this ANOVA, so if you divide this 657.97 by total of this column, that will give you R square. So if you plug in the values, you get 0.64. What does it mean? It means that the regression relationship is strong. Remember, initially I showed you a table in terms of like R. So this is R square. So if you calculate R, it will be maybe around 0.8. So that's quite high. So R square, we can say about 64% of the variability in depression can be explained by the linear relation between weight of the roller and depth of depression on the grass. And R square works very well if you are looking at simple linear regression model. But when you have multiple regression where you can add more independent variables, every time you add a variable, R square will go up. Whether that variable is significant or not, it doesn't matter. R square doesn't care about it. So that could be one of the negative points, that additional independent variables will always increase R square. So we should not rely only on R square. So the problem is that it doesn't warn against overfitting. So theoretically you can get many independent variables which are not significant and artificially inflate R square value to a very high number. So that's called overfitting. It also doesn't inform us whether the model is good or bad, whether it is statistically significant or not. So those things we do not know from R square. But the best part of R square is that interpretation is something that anybody can understand. When you say that 64% of the variability is being explained by this model, and you know that 64 is quite high, it's between 0 and 100, so that's something which everybody can understand. That's very difficult to know or assess if you look at like errors. If you simply look at the errors, because they are related to your data points, and there's no limit. It's not that the errors will be between 0 and 1, so interpretation becomes difficult. But R square has that user friendliness where you can do a good interpretation. In the same table you also saw something called adjusted R square, and it is calculated as 1 minus MSE by MST. So mean square error and mean square total, ratio of that, and 1 minus gives you adjusted R square, which comes to 0.6. One thing is that you will see earlier R square was sum of squares divided by sum of squares, SSR by SST. But adjusted R square takes into account the degrees of freedom, because we are dividing sum of squares by corresponding degrees of freedom. So that's one good thing. Another good thing is that it adjusts for predictors or your X variables, independent variables that are not significant in the model. So it makes an adjustment. It doesn't like just go up and up and up like R square, but it adjusts to things that are not significant. For a model with additional variables, a higher value of adjusted R square implies additional variables are contributing to the model. So if you are adding an extra variable and adjusted R square goes up, that means it may have some value. But if you are adding variables and adjusted R square goes down, so that's a signal that you are doing overfitting. Don't do that. Don't keep on adding value unnecessary. So adjusted R square provides the percentage of variation explained only by the independent variables that actually impact the dependent variable. So that's how it deviates from R square, and that's why sometimes, especially with multiple regression, people rely more on adjusted R square and not that much on R square, because R square will go up every time you add a variable. You can do simple linear regression without the intercept. So the only extra thing you have to do in your linear model when you are running it in R is add this -1, which means remove the first term, and it will remove. So now you have only weight, and in fact R square now goes up. Remember, it was 64%, now 87% of the variability is being explained by the model. If you compare ANOVAs, so it was significant with intercept also, it is significant without intercept also, in fact more significant. And one major difference that I mentioned earlier is residual degrees of freedom. So total data points are 10, and if we are not estimating intercept, we are estimating one less parameter. So we are only estimating the slope. So the degrees of freedom that we now have is more. It was n minus 2. In this case, it is n minus 2. When you have no intercept, it is n minus 1. So error degrees of freedom or residual degrees of freedom increase by 1 if you eliminate intercept. But it should make sense. You should not simply remove intercept for the sake of removing. In our case, we saw that the intercept was not significant. So that was one reason I removed and tried this. And the other reason was that it doesn't make sense to have a roller weight of 0. Any questions?
There was a question, what indicates moving of intercept? I'm not sure.
Moving or removing? Why do we remove intercept? So one reason I removed the intercept, if you look at this, you can see the p-value is not significant. It is not statistically significant. So, but that should not be the only reason. There may be a situation where it is not significant, but you still want to keep it in the model. Intercept is the predicted value of dependent variable when x equals 0. It is meaningful only when x can take values close to 0. So if you have x values which are close to 0, then you should not remove it. And also when it is statistically significant, because if it is statistically significant but not meaningful, in that situation I would say keep it, because it is contributing to the model in whatever way, and it is going to affect your R square if you remove it. So why not have a model which explains more variability than less variability? But if it is not significant, then there is a choice, and then you see whether it makes sense that the x values can be close to 0 or not.
Explained? I didn't catch that.
So the total has two components. The first component is the explained part. So why that variability occurs? Because of our model, like relation between depression and weight. But there are unexplained parts also. So for example, if I look at this weight, slightly more than 2.5, almost same roller weight, but at one time you have a depression which is low, and second time almost same weight gives you higher depression on grass. Now why that variability comes, some people will say God knows. And in statistical term, whatever God knows or God can explain, we as the humans we cannot explain. So that we call error. So
Okay.
if somebody says, okay, if this is the weight and this is the depression, at this weight we get this depression, and at this weight we are getting this depression. Somebody say, why this variability? Why we are getting less depression when weight is low, and why we are getting higher depression when weight is high? So we can say because of the higher weight. So that is explained part. We can explain that. But at the same weight, if there is a variability, so that cannot be explained by our model, and that becomes the error part. So that is unexplained part. Like we have a class every week at 3 o'clock, and students who are able to join live, they join at 3 o'clock, but not everyone joins at 3 o'clock. Sometimes somebody joins at 2:59 or 3:01 or 2:57. So there is a variability. Or even as a student, like as a you you may have joined one day exactly at 2:59, other day maybe 3:01. So there is some variability there. But if there is a day where you have been very consistent around 3, but there is a day where you join at 4 o'clock for whatever reason, overslept or had an interview or whatever reason. So if somebody will ask you a question, why instead of 3 you joined at 4, you will be able to explain that. There is a reason that I had an interview or whatever, I went to a seminar, I was traveling, I was late. So you will be able to give a reason, you will be able to attach explanation to it. But if somebody asks you why one day you were 2:59, other day you were 3:1, you will not be able to explain, right? That 1 minute variability is difficult to explain. God knows there may be like some reason behind it, but we don't know that. So in statistics, those kind of variability goes under error. So that's why I call this unexplained variability, and this is explained variability. So things that we can explain.
Professor.
Yeah.
So the follow-up to that is do we attribute that to randomness or some other variable that we're missing that we haven't put in? Like, is that randomness, or is that a missing variable, or is it both?
If it is randomness, we would say in roller situation, but it is not randomness in this example. So that's where residuals come into picture. So if you start seeing patterns in the residual plots, so that means there is a possibility that some of the unexplained variability could be explained by doing something to the data. And these patterns basically are hinting towards that you can improve your model if you are careful and you do something with the data. But our plots for the roller data, like, they do not indicate anything unusual. So whatever results you see, maybe we are looking at the best possible explained variability and best possible thing we can do with this data. We cannot do much. Whatever we have done, that's more than enough. But with this one, if you are fitting a linear model, these are like these plots are shouting at you and telling you that no, linear model is not good, look at us. So everybody is here like telling you or indicating in all possible ways that don't use a linear model. That's what will tell you. Yeah. So okay, if no more questions, I'm going to stop here and I will see you next week.
Thank you. Bye.
Thank you.
Bye.